All right, so welcome to the last section of chapter 3. We are done with derivatives, at least the theoretical part of derivatives. And so we move on to applications in chapter 4 here. So what we have to do, kind of go back real quick here. Derivatives of, we have something called exponential and logarithmic functions. Yep, so we're going back where we started 1.4. This stuff here. So a quick review of things we've learned so far, and then we'll jump to what we need to jump to. So just real quick here, definition, exponential function. Y is equal to b to the x. Is that right? That's an exponential function here. And then there's some conditions here. B has to be greater than 0, and b cannot be equal to 1. So it can't have negatives inside there, can't have a 0 in the exponent, and it can't have 1. Okay, that's the definition. So now some properties. Properties are b to the 0 power is 1, and b to the negative n is just the reciprocal, right? It's the reciprocal of it, so 1 over n. Cool, let's jam. And then we have something called the natural exponential function. And that one's y is e to the x. Again, very common. You know, we try to use ln and e a lot more than the other functions here in mathematics here. And so I think you guys know this here. E is approximately 3.71828, and then it's blah, blah, blah. Are we good? Okay, good there so far. Okay, still jamming with stuff here. So then the question, well, E is approximately 2.7828, blah, blah, blah. But what is E itself? What's the definition for E? E is equal to, we should say e to the 1 even if we like. It's power. So the number E comes from this little limit. Limit as x goes to infinity. 1 plus 1 over x to the x. That's where E comes from. In the world of economics, that just means if you take $1 and you give it 100% interest, like you're going to get that much money. And if you guys know something called compounding, right? Yeah. So let's say a bank gives you compounding every 6 months or something, right? So you're going to gain interest on that money in the middle of the year, and then you're going to gain some more interest later on. So now the question comes up, well, if you start compounding daily, how about if you start compounding it every single minute, every single second, every single millisecond? And if you do that, it comes out to be this number right here. So $1 at 100% interest compounded every single instant of your life will be about 2.7182.
We did numbers like that in algebra 2, didn't we?
I was not your algebra 2 teacher, but most likely should have. Okay, so with that, we got ourselves a little tiny bit of a trick here that we do, particularly for calculus here. Here's our little trick. I'm going to replace, again, maybe I could do it this way as well. I want to keep the variable x inside here, so that's my only problem here. Here's what I want to do. I want to replace x. I'm going to replace it with 1 over x. Yeah, with x with 1 over x.
So we're going to see an X will be pertaining to whatever.
And so a few things that happen. We good? Let's see. It's interesting. So let's see if I could do n over here. I guess we could do n. Let's do n just so we don't confuse. As I was doing it last night, I figure I'm going to do this here. I'm going to change it to 1 over n. We good? I'm just thinking if that's going to work real quick to get in my mind here. It should. Why? There's a little hesitation there. I'm not sure. So let's go for it here. If that is the case, first things first, limit as x goes to infinity. That's going to make the limit as 1 over n goes to where? So if x is 1 over n,
Well, does it have to be different? Since they're the same thing?
yeah, let's see. If x is going off to infinity, right? So x is getting larger and larger and larger, right?
Oh, it's getting.
1 over n,
Smaller, right?
it's going to get smaller and smaller and smaller. Are we good?
Yeah, so negative infinity?
Ooh, no. What's the opposite of negative infinity, positive infinity?
0?
0. I think I'm going to go with that. See, and here's the, wait, I might have to think about this just a little bit more. As n goes to, okay. I'll think as I go. How about that? So next question is this little piece right here. Now let's do the algebra behind it. So we're going to replace x with 1 over n in each circumstance. And if that's the case, talk to me. If this is, we're just going to take the reciprocal here. Are we good? And that's going to stay the same, right? This is going to be 1 over the flip of 1 over n, which is n over 1. We good? And I think this is what's happening in my mind here, real quick here, as I'm kind of pondering this. So notice we've done this right here, right? We've changed the variable, right? And we've changed the variable inside the function. We good? We've kind of changed two things. We good?
Mm-hmm.
And so what we're going to do is it's this guy here. We've changed the variable to 1 over n in both instances, correct? So it's not so much as 1 over the limit of 1 over n going to 0. It's just the fact that n goes to 0. We good? See if this makes sense. I'm going to write it and then we'll talk about it here. So limit as n goes to 0 of this right here is the same as the above.
The first one.
Sure. And let me see if I can explain it.
Because n is the same, so x is the same thing as 1 over n, and n is the same thing as 1 over x.
Correcto.
1 over, okay.
And so what we do is we switch two things at once, right? And it's no longer e because we actually did two things. And so what we do is we come back to the first one and say, okay, we're going to keep n as n, right? N is going to 0. So therefore, that whole piece still goes to 2.71828. We good? Okay, and I think we're done. If we have that in our place, I think we're ready to go. So the book, what the book does, it looks at it looks like, it looks at the e to the x first as the derivative, and then it has to do all these assumptions here. What we're going to do is we're going to take the derivative of ln. I guess let's go with ln first. So I need the derivative of the natural log, and it's going to be ln of x, and just see what happens here. All right, put thinking caps on. Back to our definition of derivative. Derivative definition is the limit as h goes to infinity of ln of x plus h minus ln of x over h. I believe that's the way it works. Oh, and then we have these little rules. Don't we have these little rules from ln and logs? Let's see. With a log, if you're subtracting two logs, what happens to the ratios of them? You guys remember that? Sure. So ln of A minus ln of B from algebra class, what is that?
Is it L of A minus B?
Nope.
Isn't it ln of A divided by B?
I think so, yeah. I think so.
yeah.
Yeah, subtraction changes to division. That's right. And multiplication and addition are connected, right?
Yeah.
So this is ln of A minus B. Perfect. Okay. So let's go back over here. We got some notation issues on our hands. So I'm going to have fractions upon fractions. I don't like that. So how about this? How about if I take the 1 over h, I'm going to scoot it in front. We're good there? And this is going to be ln of 8x plus h on top and a x on the bottom. Okay, are we good there?
To be clear, are we switching from N's to H's?
No, this is all H's, sorry.
All H's.
But yeah,
Oh,
N's and H's are. Okay, so remember how we used to always have this little trick that comes by? Remember those trigonometry? Equations? Well, here's a little trick. The trick is this. We're gonna, as we get to the next slide here, we're gonna let V equal to X divided by H. H divided by X, sorry. So first things first to think about is this whole concept of limits again. So talk to me here. If we're going to have V go to 0 as a limit going to 0, that will still make sure that H goes to 0, true? Because notice on top, it's the top of the fraction, right? And so if the top of a number goes to 0, we don't care what the X is, right? Because it's still going to go to 0 no matter what. Okay, so we got that in our understanding. I think we're good. So let's do this here. Let's multiply these guys together. So H now, our substitution is going to be V times X. There's our substitution. Again, a little bit of a thinking here, a little bit of abstract thinking. Okay, so I think we're moving on to the next slide here. Let's see. You guys ready for this one here? Limit as, let's do one more thing here. H goes to 0 still, 1 over H. And inside the ln, right? This is ln of, and there was an X on the bottom. I'm going to split the X's off and see if you guys agree with something looks like this. Good there? The X's got split into under the X and under the H. Now I can start substitution. Limit as H, as V now, right? As V goes to 0. it'll be 1 over Vx. One plus V inside there. That is fun. Okay, let's see what we can do now. Oh, ooh, look at this. That little X right over here. That's not part of my V stuff at all, right? So I'm going to move that 1 over X out in front completely. Now this is going to be the limit as V goes to 0. One over V, ln of 1 plus V. Every good there so far? Totally abstract. This is just moving things around.
I do not.
I'm sorry. This is my daughter because she's totally engineering major. Like theory, who cares? Where does it apply? Where does it work, right? So that's what she is. And I'm totally opposite. This is so cool. Do you see how this goes to this? And like, voila, it's magic. Okay, Dad. Hey, you know what? Remember we have a rule that says the multiplier in front of a log function, right, can become the exponent, right?
Oh, yes.
Oh, awesome. Limit, or the ln of 1 plus V goes over here. That is cool. Hold on, hold on, hold on. This is even better. I think we just did this somewhere, didn't we? Do this somewhere? Like on the previous slide? We had this little piece right here. Now here's the ends. Limit is n, right? Goes to 0. What did we say? 1 plus n to the 1 over n?
So those previously were ends. So we're looking back at what we did before, that was just to the side, it's not with the problem,
Yeah.
and now we're applying.
So for there, you could have been h's as well. So it doesn't matter, right? Either which way. Uh-huh.
The instant H's and the.
They're all the same for me. Sorry about that. Okay, so that is actually E right there. So we got to do one more step just to make sure. Look at this. It's 1 over X. Now we're going to do is we're going to scoot the limit into the ln. That's the only thing we got to do. And we know that we can scoot in limits because we had limit rules like that early on.
Wait, but, do we still have to take the limit of the, oh, we can apply the natural log after we take the limit of it, okay.
So we have 1 over X. That's great. Then we have the ln of E.
Oh my word.
And then we have voila. I think we have, oh, hold on, ln and E, don't they cancel each other out? The inverse operations of each other? That is crazy. So here's what I got. I got the derivative of ln is actually 1 over X.
Wait a second, so what?
So let's write this
I
in.
guess that looks like, yeah, because.
Now, the only condition we do have to put on this is remember ln, remember in algebra 2, guys, you guys can't take log of negative numbers, right? Logs don't work in the negative field, right? It goes like this. The graph for a log function goes like this, right? So there's nothing here. So we do have to quantify it a little bit here. We're going to say the absolute value. I think we do. Let's see. Is the absolute value? Let me just check real quick here, just to make sure, just so I don't confuse you guys, because this is cool. Implicit differentiation.
Greater than 0.
It's only going to work within, right? Because you can't have a log function that's. It just has to be greater than 0.
Can we just write that? If
As long as it's a condition, yeah. On it. So I'm going to go like this. Close those. We're going to go like this. And then the only condition is X is greater than 0. Right? We can't have negative values here. Boom. Are we good? That's so cool. I think that's really neat. So right here, here's our little formula. So Kate, for you, that says, forget that mumbo jumbo stuff. I just need to know the way to write it here. So the derivative ln of x is just 1 over x based upon the condition that x is greater than 0. Okay, next. Can we do a little bit more? See, time is just running out. It's so much fun. Next piece is this right here. So let's do a little bit more work. So agreed or disagreed? We're gonna put a few things together, which I think is cool. ln of, let's see. ln of e, right? If we do it like this right here, I think we can get away with doing it like this. Is really just log base e of e, is that right? If we want to substitute another log, another base, right? Yeah, if we want to substitute another base, remember the change of base formula from a while back ago? Right? So if we wanted to, we can actually do this here, right? Log base. Let's see, let's go back to change of base formula. It's the,
You can do whatever base you want, and you put the E that you are, the answer E up on top, and then the base E on the bottom.
the
right?
base E on the bottom. Mm-hmm. So we have this right here, right? I think I want it like that. Is that right? Oh no, it's going to be like this. It's going to be this to this, right?
But you don't have a, they're both E, aren't they?
So with this little piece right here in view, right? We want to go abstract now. So how about any log function, any base whatsoever? So what happens here is we have the extra ln that's brought into here because this b let me give it to you here, and then we'll go from there. So this is derivative of any log, and we'll do the proof next time here because I just for some reason just stumbling upon this proof here. So log base b of x, that's what I want to give. So this one's going to be 1 over x again, except what you have to do is have the little qualifier of ln of b. So for ln of e, right, that became 1, and that one disappeared on us. We didn't need it anymore. For any base function, you have that set right there. All right, and we'll do the proof for that next time, since for some reason I'm getting stuck. So there's your ln stuff, and there's your log functions here. That's great. Next, we turn our attention now to e to the x.
Don't you just flip it like, if you write that out, the derivative of log base b of x, can't you just write that?
We'll go. Now, looking at this right here, if we are going to derive the derivative formula for log base b of x, and if we change the base on it to log base e, wouldn't this just be ln of x over, sorry, log, right? And log base e of b? Talk to me, Sadie. What do you got? Is that true?
Yeah.
And so this is just ln. This would be ln of x on top, is that right? ln of b on the bottom? Good there so far, guys? And then we'll get into some problems here. So then the ln of b really is just a constant. That can be just pulled out completely. And we're just trying to take the derivative of ln of x, which we know to be already 1 over x. And there's our formula. Thank you, Sadie. That's cool. Okay, we got that one down. Because I love the way math builds upon itself. Especially when you know how it builds upon itself.
I just want you
Uh-huh.
to, sorry, in the middle line of equations on the last one to your right, how does it go from, from x over b to y? Or is that, oh, yeah.
It's ln, sorry, ln of x
All the little
and
elements,
ln of b.
it's not,
Uh-huh.
yeah. These are not closed, like a bunch of them, so yeah, it's all B.
Okay, sorry.
No, I need to write better. Okay, Kate, how are we doing? I'll get to some application questions and they're like, yes, I got this. Okay, one more thing we gotta do. Just the exact opposite, the exponential functions here. Okay, one more, we're good to go? So derivative of b to the x. So let's go exponential functions now. And still works the same way, because once we have this all taken care of, I'm going to define y equal to b to the x. And from algebra rules, I know a long time ago, I can put an ln on both sides anytime I like, right? So let's do that. Ln of y on this side, ln of, almost like cheating, isn't it? Feels like you're cheating.
Seems like half of the truths you get from just adding something and subtracting it, or doing something like that, where you're like, you didn't do anything, and yet somehow you can change it completely.
Uh-huh. And let's see, now we move this little x to the front. So we got ln of y is equal to x, ln of b. So now let's take the derivative of this, guys. So now let's take derivative of ln of y, derivative of x, ln b. All right, for this one, we're going to get ourselves, let's see, 1 over y, but we took derivative of y with respect to x. I think I did that, yep. And this one's kind of funny, because when you take rid of this, x is the only variable on the right. Is that correct? It's really x to the 1 power. So what happens here, the x disappears, and it's just ln of b.
How is the x equal to go from being an exponent to going in front?
Sure. It's the rule from logs. Log base b of x to the r becomes r. It's that little rule. So the exponent inside a log becomes the multiplier outside a log. Sure, absolutely. And please ask those questions, you guys. That's what you guys are here for. If you knew this stuff, you would not be here.
When we do the, taking the derivative, what was it called, from the last section?
Implicit differentiation?
Implicit derivation, how do you say it?
Yeah,
You have to
differentiation.
take it d over dx for both sides, right? You can't take it with respect to y on one side and with respect to x on the other.
You could, yeah. You could take with respect to any variable you want.
But then you have to write it down.
Mhm.
D over d, whatever.
Yeah, Yeah, so you may want to take it with respect to z, right? If you're doing a three-dimensional graph, right? So here's what we do. We've got to solve for dy dx. So let's multiply both sides by y. Multiply y here, y there. So dy dx is equal to y ln of b, but then hold on, y is going back to our original function. This is just b to the x, ln b. Are we good? So final answer, here it is, d over dx of an exponential function is just going to be that exponential function itself multiplied by ln b. So then you guys tell me this abstractly. We got one, we got the next one. You guys tell me what the answer to this guy is then, based upon that.
So, would it, wait. L, it would be, if we're following the same rule, it would be e to the x times ln of e, but ln of e is 1, right? So it's just e to the x? That doesn't make sense.
Wouldn't it be e to the x
Okay.
times x, because ln of e to the x goes in the front?
Oh, perfect, yeah. So in this one here, notice there's no x over here anymore, right? It's just ln of b, so it's just ln of the base only.
Oh,
So then it becomes just ln of e to the 1 power technically, because they're the 1 power now, and ln of p undo each other, so it's just that. That is weird, okay,
Can be
strange
its
stuff.
own derivative.
E to the x is its own derivative.
That seems like it wouldn't, that seems like it would work.
Should not work. Okay, so now I was trying to find a graph online that showed that. I wanted to show you e to the x as a graph. All right, you have this little piece right here. That's e to the x. And then let's say at 1 comma 2.7, right? The slope here is 2.7. And then, but I couldn't find one that actually gave the value of the slope, you know, as you're going through it, you know. I thought, oh man, that was so cool to see that.
Are there other functions like that?
No, e to the x is the only one. It's kind of like, you know how we say certain functions have certain numbers have certain properties, right? Like we say 1 is its own derivative, right? And -1 is its own derivative, but nothing else, right? So this is one of those. E to the x is its own derivative. I almost 100% sure that there's nothing else that its own derivative except e to the x.
Wow, that's really cool.
Okay, now let's start. Exercise 1. We're an hour into class. Let's do some exercises. Okay, this ln stuff actually does help us quite a bit, as we'll see in just a second here. Okay, let's go with it here. I'm going to just say find the derivative. We good? And we'll do a whole bunch of problems here. Find the a f of x is equal to e tangent of 2x. That'd be fun for starters. Okay, I am actually finally feeling the heat of the heater there. I'm finally warming up. This is good. Okay, and we got to get to a place here eventually here.
On that,
So
are we somehow doing like, the chain or something?
yeah, chain rule comes into play right away. And so I'm going to go with it here. You guys good, good, good? Let's go with it. So e to the derivative f of x is, let's see, first things first is its own little thing, right? E to the x is going to be exactly the same as it is before. So this is going to be e to the tangent of 2x. Exactly as before, no changes whatsoever. Okay, we also know there's a 1 here, right? It's ln of b, right, which goes away, right? Then afterwards, then yes, we still have a multiplier of everything else that happens on this side here. So derivative of tangent. And if you want to put into different pieces, if you're like, man, that's too much for me, Mr. Ngio, then you also can do this. That's no problem. Just kind of put everything else inside the derivative notation, right? And then as you go through the pieces, then you get to the point of going through every single one. So that means e to the tangent of 2x, and then derivative tangent, guys. Secant squared, perfect, of the same stuff inside. And then do we still need to take any derivatives?
We won't do any.
Yes, uh-huh.
It's just two.
Absolutely. So there's a triple chain rule here, right? Technically.
And the funny thing is, like, the first chain rule, you're supposed to take the derivative of e to the everything else and leave that inside of it. The derivative of e is just leaving it inside it. So, like,
Correct.
there's
Uh-huh.
two reasons why you would leave tangent 2x inside there. So does that count?
Yes, absolutely.
I guess because you can pretend you didn't actually take the derivative of the inside, even though you did. It was just x. You just replaced it, even though it would be that anyways.
Mhm. Okay, we good? And let's see, 15 minutes? Yeah, we can probably do the rest of it, 15 minutes. Okay, you guys please ask the questions if you need it, okay? We'll
Makes
kind
sense.
of- okay.
That's surprised, but that's okay.
We had to go through the abstract thinking here to get here. That's really good. Okay, Kate, talk to me. We good now?
Yeah.
Okay, and again, ask the questions here. This is so much fun as well, because I've taught classes of 80. I think 86, I think, was the highest class I taught. So teaching a class of 4, this is so fun. All right, I'm going to just hint at it, something called quotient rule, but other than that, all yours, go. Oh, that's right. And then, 25 over 3, 25 over 8. And Sadie, I did look up on 3.8 on the lecture. Yeah, actually it does, on the online book, it actually does say 25 over, there's a discrepancy there, so I'm gonna look that up.
It's funny, I wonder what, I wonder if there's other things like that.
Hopefully not too much. Okay, let's go with it here. Quotient rule, let you guys start off first. Finding the derivative.
Don't we have to do the chain rule also with that x squared?
So you can always put dy dx if you need to, right? Wherever you need. And this one's kind of funny. Real quick, we should mention this. So if you take the derivative of this right here, you can go one of two ways. You can actually say dy prime, which is a way to say derivative. Or you can say dy dx. You can explicitly say that you're taking derivative with respect to x, or you can just say y prime. Any one of those work just fine. I'm going to put dy dx. All right, and then off to the side, I'm going to put my quotient rule derivative, right? Boom. It'll be a derivative of the first times the second minus derivative of second times the first divided by second squared. So if you want to write down the formula, it should almost become second nature eventually to you guys. Okay, so let's take the derivative here. So derivative of e to the x squared is going to be the same exact thing. Good there? Multiplied by the derivative of that exponent, which is 2x. Okay, that's the function, that's the top function. Then we also have this, the x itself that's coming from the bottom, that's g. That's the bottom g of x. Cool, minus sign. Then it's going to be, oh, even better. How about, that's just gonna be a 1 for the derivative of that, and it's just the second over this guy squared.
Where does the 2x on top?
It's for the derivative of this guy here. it's the derivative of x squared would be 2x. Okay, the only other thing that we normally kind of sort of do here is if you have a factor on top, you can just factor that thing out and just kind of leave it e to the x squared. That'll be there. This will be 2x squared minus 1 over x squared. And that's a nice, just sort of pretty way of seeing it.
Will the application chapter just be using all these things to do real world problems?
Uh-huh. And so just to give you a flavor of it, let's see, first of all, it's not, graphs would be a good one. Just so if you see a graph, you can take the derivative of the graph, you can take the other one. Position, velocity, acceleration, maximizing something, minimizing something. Now that we can figure out the derivatives, normally we say when maximizing something is when you're going up and the derivative is 0, right? Now you're going to go down. So then you've maximized that piece there. Minimizing cost, same thing, except the downward flow. And so there's that. That's some physics problems and stuff. Okay, we got 10 minutes. Let's go with it here. So we're on C. Can you guys do this one for me? Take the derivative of ln of x cubed plus 3x minus 4, all yours. All right, so dy dx for me is going to be, what do you guys say? That whole big old thing on the bottom, is that right? Just a little bit of a chain rule, but not by much. Yeah. Okay, Taya and Kate, are you guys good here with this one right here? I'm putting this all in the bottom. Right, because that's what it says, right? Derivative of ln of x is 1 over x, right? Okay, then we're going to do is we're going to take the derivative on top. So it's the derivative of this guy here. So if we want to still take this, it's still going to be this right here. And what do you guys say? 3x squared maybe plus 3? Okay, maybe it'll be helpful off to the side here. Just, and if you need to go back or not here, right? ln of x is 1 over x, right? As a rule. The derivative of, you almost have to, in my mind, I think, you almost have to go back and make sure you've written down the rules. I'll send you the formula sheet. Did I send you guys a formula sheet yet or no? Yeah, okay. I'll send you the formula sheet, but it's almost good just to have the rules off to the side. You're like, okay, I got this. Bring it in. Okay, D. So now let's start with the tougher ones here. On your mark, it's set. And oh yeah, no, we still need to do another ln of this guy here. What? There it is. That's a fun ln. Okay. Yeah, I think we'll. Okay, this one, real quick here. I wanted you guys to stop though. It's going to get really complicated here because you're going to have first of all, complex fraction when you start off, right? Then you're going to have. Yes. Okay, how can we easy this out on us here? Oh, you know what? Hold on. Don't I have like a little relationship that says if I have two things that are a ratio inside the log, I can make them as a subtraction outside the log? Is that okay? I think I know this little rule from algebra. In fact, I know some more. That little x squared times sine x, can I expand it out anymore? I think so. I can expand it out like this. Okay, so is this going to be a lot easier to take derivative of? Cool, so we've expanded it out. Hey, that's why we did all those expansions of logs, or else this would have been crazy. Okay, so now can you take the derivative of each of those individually? That's what you want to do. And you do not have to combine them together because there won't be a sense of combining them together.
You guys missing such a good day.
Okay, are we good? Now ready for the derivative? Okay, are we good now?
Yeah.
Ready for the derivative. So ln of x squared, I'm going to take the derivative of that guy first. That's going to be 1 over x squared multiplied by 2x plus sign. Sine, so the 1 over sine multiplied by cosine. Minus sign here. Now, kind of careful with this one here. Remember with subtractions, if it turns out to be, it's going to jump into two different forms, right? We got to be mindful of that here. So this would be, let's see, 1, that still would be okay. 2x plus 1 on the bottom, right? Multiplied by 2. Hey, what do you guys say? Not that bad? Not that bad. This x squared and this x, those can be reduced. So how about just a 2 over x? Ooh, back to trig. What's cosine over sine? Cotangent, I like that. Minus, and then this one we'll leave exactly the same. That's okay. Boom, 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 boom. Done. There it is. Let's see what we got here. Yep. Good. Okay, 2 toughies. You guys ready for the toughies? So what it allows us to do, and well, they introduced it as something called logarithmic differentiation. This is actually a process now. Are you guys good with this one? Because we know logs, it has allowed us to go into a whole other field of differentiation. Yep, and it's actually a method all by itself. We're good. I guess I should give it a title here. It's called logarithmic differentiation. Da, 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 da. And we're going to take the derivative of this guy. Okay, so first of all, let's think about this here. I have something trapped in the base and I have something trapped in the exponent. That would be crazy. We good? Because there's no rules for it
Oh. Can we do
anymore.
like one of those where you take the log of both, or change it into a log and then take the derivative of both sides?
Perfect. Yeah, just like we did before. So what we're going to do, we're going to take the ln of both sides, and we like to work with ln. And that's what logarithmic differentiation is all about right here. What we do is we take the ln of both sides. That there. And again, it's what Kate was asking the other day, the other time, sorry, is we can move this tangent of x where now? All the way in front, is that right? Boom, we got that. And we have ourselves a product rule here. So what it allowed us to do, instead of being trapped in an exponent, it allowed that to be just a product rule between two things. Cool, let's go with it here. So I'm going to take the derivative of ln of y, which is 1 over y, dy dx is equal to, and can you guys help me out here? Product rule, derivative of fg makes derivative of the first times the second plus derivative of the second times the first. I think we said it today. Derivative of tangent is secant squared, is that right? So here is the big stuff here. This is derivative of tangent is secant squared. Everything else remains the same. Dun, da, 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 da. Plus, now let the fun begin. Now it's going to be the derivative of ln, which is 1 over 2x to the 4th plus 1 times the derivative of that guy. How about to the 3rd? Perfect. Times the back number there. Almost done. With a minute left, we move that y over to the other side still. So it becomes dy dx is equal to y times, and let's clean this up as well. Let's see, I think this portion is okay. No cleaning needed here. This guy's going to become the 8x cubed in front, or on top, sorry. Bum, bum, bum. Boom. One more step. What do we got to do? What is that one more step? We got to convert the y back to its original form, right? So one more step. This little y becomes back to what it was here. Okay, you guys good? Final answer, here it is, dy dx. And I'm just converting back. So this is 2x to the 4th plus 1 to tangent of x, and this whole piece exactly how it was before.
What even is the graph of that?
I have no clue. I think part of it is that in mathematics, we just, especially in theoretical pieces, right? We just take it to the craziness, right? But then we deal with regular stuff. It's not going to be as crazy.
Oh, regular stuff is boring.
Okay, and we are done. Da, 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 da. Ms. Bear, please come on in. We are done.